Good to see you all. I think it's by this time you're all aware of, I think, the observational fundamentals of some astronomy from the yesterday classes as well as yesterday's lectures as well as today's lecture. In this lecture, I try to cover something about the stars and galaxies. I'll try to give a brief overview of it. As it is always good to have an interactive way so that it will be less, it will be more interesting. So you can see that this is one figure. It's like it's just like a curiosity. Like the people are, many of us, when we are kids, we used to just see on the sky and then try to understand what are there on the sky. So this is actually a real picture which is taken in the northern countries, where you can see something here in the greenish color, and then you can see various dots, nothing but stars. So that is the first question which people try to look up. They wanted to ask themselves that what are there on the sky. So I just mentioned it. The sky means for astronomers is basically a lab that many of us in the masters or undergrads, we just go to our labs and then do our experiments. And I think in UZ, PZ, we study physics as well as chemistry. So basically astronomy is nothing but we just, it's an applications. So application of physics or chemistry. So that's the same. That's it. That's all. So, but then when we talk about the sky, actually, as we know, there is no limit for it. So I'll try to give you a flavor, though people have already introduced various things. Maybe some repetition may be there in my lecture, but I try to give a flow of the way what we do, how do we study objects on sky. So this question is actually one should ask themselves. So that's, I just leave it to every one of you. It's like what you see on sky. So let me go further. This is basically not the sky that we see from any of our cities or not from India. This is basically very close to the pole. So that's why you could see that this is called aurora. So I think some of you may be knowing aurora, but how it happens is something like you see that Earth has some magnetic fields. So it's actually is well structured. I don't know like how it is well structured, and it can actually help itself. I mean to say Earth can help itself from any damages which will be caused by our host sun. So there is a lot of very energetic particles comes over there, and which we cannot take it up. So somehow our atmosphere is so well structured that it doesn't allow us that extreme ultraviolet, so that we will just burn ourselves. And also like there are very energetic particles which doesn't come to us, and our magnetic field is actually blocking them. And then though we see it looks so beautiful, the different colors, but I think you should be aware that it actually causes a lot of damages to the electronics. And because of this auroras, there is, I think you can say the black days you can in Canada, or the city is very close to the poles. So it just shuts the power. So it looks beautiful, but it is very, it can damage or some systems which is developed on the Earth. So let us go forward. So the same thing, the sky. I think if you ask any astronomers, they just take you to the sky. That's so. But this night sky, Yeah. So it's, for me, night sky is fascinating. But I think many of you people might not have seen this sky. So this I'm showing the picture. It's not that I've taken from, not taken from the Google itself, but then if we go to Himalayas, where our observatory is there, actually we see the sky like this. So maybe if you see such skies, certainly like you will feel it's wow. So this is the sky from our northern hemisphere, like which is the Leh Ladakh. If you go to deep inside Himalayas, then you will see such sky. And you see that this is actually, this is something like, it looks like it's very dusty. This is what you expect in Bangalore like kind of cities. There's so much of pollution. You will first see dust and then you see something else. But then here, this dust is a real, where in our center of galaxies, we actually have a lot of dust. And dust is important because dust is nothing but it's molecules. So the dust and gas together in the clouds, it forms various stars and various things. So the dust is always there in the center of the Milky Way. And that is what we see from here. So this is, when I say northern hemisphere, I think many of you might be aware of when I say northern hemisphere and the southern hemisphere. So we are at the, I think, latitude of close to 12 or 10. But whereas Himalayas, which is, this place is at a latitude of 34 degrees. I think tomorrow morning class, I think you will come to know about whatever the spherical astronomy that we call. But this latitude is longitude is known to everyone, because we know any of our places, longitude and latitude is the one which decides the location of on Earth. But then that you convert into, when you convert that into the spherical coordinates or the whatever the sky coordinates, then you can locate your object, what you see on the sky. So that is called array and declination. So which you will learn tomorrow morning. So this I want to show you that this is the sky that we see from the Hanley, and I'm sure you might have seen, I mean, different colors of the stars, which we come to the next slides. And okay. So this is also a beautiful sky, which your Milky Way looks like this, but then this is the pic which is taken from the southern hemisphere of our Earth, which is taken at Chile. In Chile, you will see the southern sky. So in the southern sky also, you will see that your Milky Way, beautiful Milky Way, and then you will see these are all very nearby galaxies, which is not our galaxy. So this is all our galaxy, but then you will see some of the small dwarf galaxies. So this is what we can't see through a naked eye, but then some of them actually we can see. So we will, in coming slides, we will see that what is there on the sky. Now we just say that this is all very qualitative statement that, okay, we see stars, galaxies, everything. But basically what we see is nothing but we are seeing the entire universe. So we are just standing on our Earth, and then we are just, the entire universe is there out. And what is the universe? I don't know how many you ask the questions to yourself. And when we go to, if I remember when I was a student, we used to go to various places for outreach. So then we used to ask, many people used to ask questions that, okay, what do we see on sky? Then people say that, okay, we see some planets, we see moon. So they say, beyond that, I don't want to know. So I'm okay with my sun, my earth, and my planets, so I know them. So I don't know what it is there. So, but there are a lot of people don't know what really is there. Even astronomers doesn't know what you call kind of 80% of universe, what it is made of We also don't know. We only know from these calculations, you can see that this is 100% of the entire whatever energy and matter. If you divide, the 69% is called a dark energy. So you really don't know what energy it is, and what form of this energy is, we don't know. And the total matter is around 30%. So among 30%, you have 80% is called dark matter. It doesn't apply any standard physics model. So we don't know what this matter is made up of. And 20% of this 30% is the one which we know, which actually applies the standard standard atomic models or something. So if you calculate these numbers, so can you tell us how much percentage of matter that we know? 4%. So that means basically what even you call astronomers trying to understand. So we all try to understand that 4% matter. So imagine that another 96% no one knows now. So what I'm trying to tell you is there are a lot of open questions. There are a lot of unanswered questions. Is still there. It's unlimited. Questions are there. So that means if you keep asking one question, you basically won't end up in an answer. You basically end up in another question. So that is the way, that is what the universe is. But many people believe that like how our earth is very well structured. So even the entire universe also might have been well structured, but it is us, we are not able to understand them. So we need to put more efforts and join more brains just to understand them. So that's what the research in astronomy and astrophysics is about. So and we apply our standard physics, and of course the research in the basic physics, like also its fundamental physics also go on. So then only you will understand what are different varieties of matter which we can add it up, and then we can understand this universe. So leave it there. So let us discuss more on whatever the 4% matter that we know. And among the 4%, it is easy to explain you is all 4% matter is divided into the dust and gas. Consider you don't have anything. It's a space. It's empty space you call. So that empty space is nothing but either it is a matter of dust or some gas. And stars. So stars like sun. So like that you will have billions of stars that you have. And galaxies. So galaxies is nothing but like when you say our solar system, you have sun at the center and you have a planets around it. So we call it as a solar system. So the same thing like you have called a galaxy. Our galaxy is called Milky Way. So it's a Milky Way, just a system. So you have something at the center and you have many stars around it. So if you go further, it's the same thing. So that's the fundamental physics that we understand. That okay, you need to follow some Kepler's laws or something. So that is the way like our solar system is, and also our Milky Way is. So that's a general way of understanding. It's very simple. So these three things we will see. We will try to understand little more about the stars and maybe our Milky Way, and not much about the dust and gas, but because the dust and gas is in between the stars, as well as every star has its own atmosphere. Like our earth has an atmosphere, so that is of gas and dust. A little amount of dust, but more gas. So even for the stars also you have some amount of gas and dust. So we mostly try to understand stars and little bit I'll touch about the galaxies. So if I tell you that that's the universe, but then if we try to understand what is the origin of the universe, I think we don't have an answer. But then what is the evolution of the universe? So that is what we try to understand. In a common term, many people, if I put it in a different way, like what is the origin of our life? Or what is the origin of earth? So there are a lot of origins we really don't know. Okay, so but we try to understand how we evolve. So we are actually like dating back, like we are going back and trying to understand its origin. So the same way, if like the how humans evolved, so that is a branch of people try to understand the evolution of humans. So because we cannot see one cannot see the entire life of human and then see how he is evolved, because among humans also you have varieties of, each human may be a different. So still we don't know like how RNA, DNA evolves. So we also don't know. So it's also, so that is the way among the stars also. Like you have a varieties of stars, but then you cannot stick to one star. It lives in 1 billion and then you keep on track on it and then we don't know. So, or if really someone build a time machine, maybe I will just go travel from here to there and then I'll tell you the solution. So that is also not possible. So this is a simple picture which tells us that, so this is the way our universe evolved. Okay, so there are a lot of people ask questions here, really there is a Big Bang. So that is the origin of the universe, that's so called. So somewhere something has to start. So this is what the standard cosmologists, they introduce the cosmological model where the Big Bang starts and then from there on our universe got expanded. I think in tomorrow or after tomorrow you will be hearing about the cosmology talk. So you will hear most in the first few minutes of the universe in much more in detail. So then you can see that then you have some first stars are formed, like first galaxies are formed, and this is a few 100 million years. And then because we call the universe is accelerating. Okay. So one can ask like why universe is accelerating, maybe it's a static. So people have observed different objects at a different epoch and they could understand that it is actually like universe is expanding. So whatever the statements that we give, it's basically has been research has shown the evidences. So that is the way we understand this evolution of the universe. So after a few billion years, it seems like your universe is expanding, and then a kind of a 9 billion years people thought and some planets have formed. Okay, but then but anyone knows that what is the age of our Earth? 4 billion years. So then why I am saying there's a 9 billion years there is something has formed. But this 9 billion years actually is, I'm just looking from there, not from this side. So during, like if we calculate our age is something around 13.5 billion years. So it says that maybe like 4.5 billion years, our solar system has formed. But still that is not accurate, but we see that there are a lot of planetary systems which exists in other stars too. So I don't know how many people believe that there must be a similar solar system exists over the universe. You believe? And so others don't believe that there must be a solar system is unique.
Just because we don't know, we cannot say that it doesn't exist.
Okay.
We are not equipped with good technology.
So that is one thing that, okay, our solar system doesn't exist, but then now we believe that there must be a planets exist. Okay, then what about how many people believe that human kind of lives exists on other planets? You believe? Okay, so some of them believe that there must be a similar kind of, and can I twist that question that how many people thinks that there will be a life exists on other planets? Yeah, that's good. So, I mean, for others who have not raised hands, they must be thinking that when I say life, life could be in the any form, right? It doesn't need to be like how we are structured. So maybe we are more, because maybe we are more what you called, Earth has a certain compositions. So we are much stronger with whatever phosphorus or something, which is, and we are like oxygen based guys. Huh? It's oxygen based life or something like that.
And also the other environments from the other planets, whatever the extra advantages are.
Yeah. So that is, and also maybe, I mean,
Our definition of life is completely different.
yeah, our definition of life is based on how whatever Earth has given to us, and one should believe that. So these are all not like what you call just statement. This is all actually you can feel it here. See, for example, our Earth. Imagine that if the Earth was born in this era, a few hundred million years means 12 billion years back. For example, our Earth has formed. Then I'll tell you that in the first few years of this particular Big Bang, you will not have any heavy metals in the universe. You will have a hydrogen and helium is the rich, a very small amount of lithium. So that is the way the universe was formed. And you imagine if our Earth was formed that time, and I'm sure we'll not have gold, diamonds, and whatever the lithium ion batteries that we use, so huge, nothing. So in that way, maybe we are lucky that we are formed at a later phase. So that is called, I'm saying, the life. But who raised the hands that they believe the life exists on the other planets? So I would agree that it all depends on what kind of planet it is. And another question I will ask you, that how many people thinks that this human life will continue? For how long?
As it is conducive for life. As long as it is conducive for life.
Life. Okay. So imagine, like, for example, now the sun and earth distance is the same. But for example, the sun has been increased. And now the present temperature, I think we are seeing it, right? For example, when we are kids, I think Bangalore temperature never reaches, people say, the 25 degrees or 30 degrees. Your global warming increased 1, 2, 3 degrees now. And now it reached to on Earth you can see like 55 degrees, which is the hottest place. Imagine it increased 100 degrees. So if at all, like that, our Earth environment will not be suitable for such kind of humans maybe. But then maybe like how we evolved from certain species and now we reach to this species, and maybe like we will have a different species.
Just selection.
Yeah, that's like we will be more strong with different elements than the whatever we have now. But in practicality, you see that, I don't know how much true it is. Medical people can tell us that, 100 years back, people are much more stronger with their bones than us. So bone strength is much higher for them. So in this way, the evolution. So this is what when I was just trying to explain to the people who are in a confusion that, what kind of life that we have. And also like people who raise that, such kind of human life on other planets, whether exists or not. For that, you imagine that such kind of human evolutionary period is maybe a much smaller compared to the life of the Earth. So that means such kind of life only could exist for a span of life. Similarly, you will have maybe having a planets, but the span of that life we are missing. So in that way, like whoever raising the hands for their life, such life on other planets. So, but I'm sure I'm not giving you 100% answer that that's exists, but this is what the belief that what people have. It's not just a belief that based on the whatever evidences that we see. So that way actually like our Earth is lucky, and Earth also is like a rocky planet. If would have born on Jupiter or something, maybe only gas, nothing, no metals. So it is also that way. Like so the human, whatever the life form, is also highly depend on your whatever the planet. And also our host also has to support us. So it's the sun. So if sun doesn't behave, if it behaves properly, then we are all fine. But if sun, it keeps on erupting heavy materials, it's called whatever CMEs and all. Maybe you will hear tomorrow's solar talk. So if it is less active, I think we are quite fine. So if it is more than what we expect, there's too much active, then it would have been a problem for Earth. So I mean to say, so this is all about when we start, if we talk about the planets and all, the fundamental things comes like about the hosts, that is stars. Now when we talk about sun, so and the different stars, so that's why the stars are highly important, how it forms, and during the formation itself it allows its kids to form. So that is what a certain branch of researchers are trying to understand, so that they know how they formed and then how they evolved. And imagine like another few million years, sun grows. Maybe we won't see that, but then imagine what happened to our planets. So how many people will say that whether the planet or Earth will eaten by sun or it will kick out? Eaten by planet. Sorry, eaten by sun. Anyone else? What do you think? It will be engulfed by the planet, by the sun. Because it will swell. It will swell. So there's only two possibilities, that either it will take inside or it will kick out of the orbit. I don't know if anyone has anything else.
Then general relativity won't allow that to happen, that it will kick out, right? Because mass is more, so the probability of those planets coming into it will be more larger, I guess.
But you see the time scales. For example, sun expands slowly. Then consider it pushing its orbits further. So I'm talking about time scales are like in the million years or something. So imagine there's a possibility I'm talking. So this is the one set of people believes that it will just push you like this, and then that also why they say is, I'll tell you the stellar evolution. Even the end stage of the stars still hosts planets. That means somehow they survived. How they survived, that's a different story. Try to understand. But then otherwise, some survived. People identified it. So that's why they keep a possibility that it will just pushes your just orbit, but then it will stay there. So that is the way, is a possibility. The another possibility is that it will just take one by one. Whenever it's hungry, then it will take it. That's the one possibility. There's a third possibility. What it could be the third possibility? Anyone can guess? Okay, the third possibility is like, as I said before, like it will generate too much of heat. So then what happens if we generate too much of heat? It will just like burn into ashes, but it will stay it will again go back to its original shape, like a dust. It became a dust or something. It is like your ornaments are just putting so much heat and it became the original gold, like that. So that is another possibility. So these are all the possibilities that people are trying to understand. So people try to understand what is the origin of it and what is the evolution and what is the fate of it. So that is the way people are trying to, now it's like thousands of planets are discovered, and you can see them in a different around different varieties of the stars. And I will show you as an evolution, then you can understand that even you will see a end stage of the stars. Okay, so that is what here I think what do you call the resolution is not very good here, but then the statement here is like end of life on Earth. So this is what they believe in a 20 billion years. So it's like a 13 in another few billion years, I think end of life. That's what, this is just a prediction, some people.
End of life on Earth.
Yeah. That's the statement there. So in a simple picture, this is what the universe is evolving. But when you get into each and everything detail, then you will understand what are the problems and how to understand them. But I will try to give you overview of the stars from here. Yeah. So, yeah, when I say how do we study? So as I said, as I know that there are some first stars are formed here, which is very close to the universe formation, and now I am here. So what is a branch of people do is, it's better, I'll pick a star which is very younger than our sun, and then I will go back with the time, and then I'll pick the stars at different ages, which is where I'll find out my first stars, and then I will see what are their dynamics and what are their chemistry, and then I can actually reach to very close to the universe, what it is. So I'm telling one category of people do that, and another category of people they study a different galaxies. It's a bulk of stars. So I'll pick the stars for now, and then so I think many of you have seen this picture. So this is sun. Sun or star is not as good as how we see from here. It looks so calm, but then you will see that it is so violent in its shape. So the star structure is, you can see there is a core over here, and you have a radiative zone and you have a convective zone. So this is simple physics, radiation and convection, that every one of you knows. And you have a photosphere, which is like our atmosphere. You have a atmosphere very close to your star or sun, which is called photosphere. And there is called a chromosphere. So it's like our Earth has a different atmospheric levels. So like that, you have the chromosphere, which is slightly hotter than photosphere, and you have it's called corona, which is slightly violent in temperatures. When I call as a physicist, we understand in terms of temperatures in a better way. This is actually a structure of sun and sun-like stars, which are like we call as a one solar mass. Any stars which are very similar to the sun, we call as a one solar mass. As I'm sure, like when I talk about the mass, or which is in the order of 10 power something kgs, this is not in the end. Also temperatures, when I talk, the temperatures are all like thousands to millions Kelvin. So the scales are, so you see, I was just talking about this star, which is very close to this orange or yellowish, which is very similar like sun. But then the size indicates the mass, roughly. This is a cartoon, but I am trying to explain it. So this is one seems to be like slightly higher mass, and then this is a lower mass. And I think you can understand this is called convection and this is called radiation. So it's basically when it is very smaller mass, basically the core when I say that is very important because that is the where your fuel burns and that is like an energy source. I think in the morning lecture you might have understood that in the nucleosynthesis. So this is the place where the fuel burns. It's a very dense material, but then it will spread over, your energy will transport, and then that is what ultimately surface that what we see. So this is a smaller one where is a fully convective, and where is the sun-like stars you have a radiative and as well as the convective, and the heavier masses you have a convective core and also you have a radiative envelopes. So, and I think as you have known everything from the morning lecture, I am just repeating this. So this is nothing but your central fuel. So this is what very important. So if your fuel is burnt, and then that means it's just into the ashes. Or if your fuel doesn't burn, it will just become a degenerate. It's like a rigid degenerate body. So here I have seen hydrogen fusion, helium fusion. So these are all from hydrogen to iron. So this particular material will fuse into the heavier elements, and then that keeps on burning. So as it keeps on burning, it will generate your energy, and then star keeps growing and growing and all. This is highly mass dependent. So some stars only can burn hydrogen, and it converts into the helium, but then helium fusion doesn't happen. And then some very massive stars can burn every element because its central core temperature will be in the order of 10 power 8 Kelvin or so. It's much higher. So they can burn up to the iron. Okay. So I'm not talking much detail about how we categorize a low mass, an intermediate mass, and the higher masses. Okay. So if I tell you roughly, maybe less than 2 solar masses we call as a lower masses, maybe from 3 to 5 or 6 up to 7 we can call as intermediate mass, and above 8 to something we call as heavier masses. See, this is all like a general way of, I'm just telling you in very vague way, but when you go when you estimate your masses of your stars, then you really understand the central fuel also will tell you that what kind of masses it is. Yeah, so previously I was showing blue, yellow and red varieties of colors of the stars. So I'm sure, I think in the morning lecture, the first picture, I think you will just see that. I don't think even if you see a clear sky in the night, I'm sure you will be watching a different colors of the stars. So like astronomers somehow knows these names, like because these are the brightest stars that you will see on sky. So I'm sure it is beyond people try to understand the each stars and all. I think the basic understanding of the constellations everyone knows, and everyone knows their stars, their what you call star rasi, or all this zodiac signs and all those things. Everyone remembers because we want that in various occasions. But then when you try to understand them, that why when someone gives me a born star something and then zodiac sign something, it is nothing but it's all on the sky. If you when I go to this Ladakh people, I heard one documentary from the local people were talking to them, like they are very old people are there, and they were trying to tell us that we never know the exact, we never had a watches, or we never had this sophisticated stuff, but then everything what they do is based on they look at the sky. Their harvesting, their whatever, when their cattle goes for grazing, Now also I don't think they will see anything. There are a lot of people very remotely, they still see the sky. And sky is so clear that you will see all constellations very clearly. So what I mean to say that whatever that our horoscope, there are various things comes, it's actually in older generations, they are real actually. They actually see the sky and then do various things. So I mean to say that some of these bright stars are actually on some of these constellations. So, and they also know that this color of the stars. Forget about that history, but let us come to physics, which is really behind this, why these are all colors, different colors that we see. You can see that the blue, which shows that it is the hottest, for example, is at 25,000 Kelvin, and then you see that bluish white, and then yellow, and then orange, and the red. Red seems to be like the coldest. So now, how I can connect this color to the temperature? I think many of you know that. Anyone can tell us like what is the relation between the color and the temperature? Yeah, but what? Color when I say, and then it's a wavelength. Yeah, so your lambda is proportional to your T, which is maybe Venus or something. So when you see this, some of the stars, actually it emits the electromagnetic spectrum, and it actually emits in all wavelengths. So that means at particular wavelengths it will peak. So that's our basic physics says that, okay, just peaking at a certain wavelength, and then just we corresponds our lambda to temperature, and then this star will be the certain temperature. So that is the first level of understanding what is the temperature of the star is. Good. So, and then further we go after this. So this is the way we understand the color and temperature. So for that you really need electromagnetic spectrum of it. That means basically light, how it's distributed. So that is the way we study the color and the temperature. So once you know the color and the temperature, so that is actually an important property of the stars, that once we understand the temperature of the star or the color of the star, some of these great people like Hertzsprung and Russell and these people actually put all the stars together in one diagram so that it will be easy for us to understand the evolution of the stars. So now if you see this is a diagram, it looks very simple. So there's a temperature in the x-axis. It tells you that 30,000 Kelvin to 3,000 Kelvin, and now it is suddenly working. Okay. So you see that here the hottest to the coolest, the color from blue to the red. And this is all we talk about now, the x-axis. X-axis is absolutely fine. Now you understood the color and temperatures. So now in the y-axis, here actually I am showing you it is called luminosity. So I am sure everyone knows the term of the luminosity. But when it comes to the stars, so we know that star emits in the entire electromagnetic spectrum, and you integrate it. So you integrate it, but then how do we integrate it? And integrated flux, and also we need another parameter. We need to know that how far it is. So that is another important parameter. If you know the distance of the star and you know its integrated flux, you can get the luminosities. So a simple fundamental parameters. So once you have these fundamental parameters of temperature and luminosity, you can put them on this HR diagram. So we call HR diagram. So then you will see that different stars will locate in at different places. And this simple diagram has a multiple informations. You see that the stars are going from red to the blue. It tells you that it's increasing with the mass. So the massive stars sits at very hotter temperatures and also the higher luminosity. Why it's higher luminosity? Because this all central source is burning. So you have a lot of material at the center. The more fuel, more energy. So that is the way this diagram tells you the mass. And you can see that this looks smaller, that looks slightly bigger. That means radius. So basically your radius also you will understand from here. And I'm sure you people know the relation between temperature, radius and luminosity. Yes. Oh yeah. So, but so that means, see, you can see that your r square and the t4th. So that means if you know the radius of the star and you know the temperature and you know the luminosity, so other way around. So it means, I think these all researchers made our life very simple so that we can understand it. So that is the way you can actually get it here. I'll tell you, these are all the stars which you call the mass information you are getting, and you will see the radius information. So for example, the stars sitting here, they are very hot, but then their radius is very small. That means they are very dense. So these stars are called as white dwarfs, which are the end stage of the stars. Okay, and these are all the main sequence stars, which are they're starting their life. And then when you see the stars are moving to slightly increasing the radius, but then the temperature are cooler. I would say other way around, you have a luminosity is higher and your temperature is cooler. So you just have to play with this L, T, R, and then you will know that which star can put it up where on the HR diagram. And if at all you see that the star's radius is higher and luminosity is higher, but its temperature is lower, that means the star has evolved. So in that way, this is the diagram which tells you actually the evolution of the stars. And you can see that there are some of these smaller mass stars, they just leave its main sequence to further. So this is what our sun will take. You can see the sun here. So sun will take this path soon. I mean, at least from this diagram, you can see that this will go like this. And then massive stars will take to this supergiant, it will look huge. And I don't know whether you are able to see this radius curve is actually like, this is a 1 solar radius and this is a 10 solar radius curve. This is 10 power 200 solar radius and this is a 1000 solar radius. And I don't know whether you heard about this particular star. Now it is sitting at 1000 solar radius. Imagine like your 1000 suns. So it is already, I think, it's already swelled enough. So it may explode at any time.
You can see that directly.
As a supernovae. So that is like one of the possible candidates. It's actually is Betelgeuse. So that is one possible candidate that in our lifetime, maybe we may see it's exploding. I don't know whether it's good or bad, but then this is for astronomers is always good. Any fascinating thing. So this is what illustration which I am trying to tell you. This I showed, but then this is the picture of the same HR diagram where each dots is a one star. It is observed. So this is actually a real picture of the observed stars. So you get a stars and then you have the colors. It's like when I say B minus I, this is called color. Means like you observe the star in one filter and you take up the another filter. So then that becomes like a color. And then this is called the magnitude. I mean, it's called absolute magnitude. Absolute magnitude means, so there is another thing which you might have, maybe tomorrow they will say, it's called whatever we get the flux from the star and then we estimate it, it is called the apparent magnitude. But then you need to know exactly what is its absolute magnitude. For that you need to know the information about the distance. Otherwise, like a closest...
Just like a refraction.
Yeah, that's the thing. So you will see that it is so bright, it may be very close, that's why it is looking so brighter. Though it is like far away, that's why it looks fainter. Maybe it is better than whatever we see. So the distance is the one of the important parameter to get the absolute magnitude of the star. Okay, then only these all things works. Okay, so these are all actually measured, and it also has a different sequence. So I'm just trying to show you that this is an illustration. It is not just an illustration that I'm showing to you. So this is basically, that's what we study. So we observe, our observations will tell us all these things. The previous slide is much easier slide, and this slide is little complicated in the sense this is the real evolution of the stars. I mean, I'll try to give you briefly. So it's all technical terms. I will use it for at least for this slide. So this is actually the molecular cloud. So this is the place where the stars take its birth. So this is the birthplace. Okay. How the stars forms is one lecture. Okay. A simple way we are trying to tell you is that it has its collapse, and then we know that it has some rotation. This is some of the physics is applied there, and finally it took a shape, nice shape of a star. Okay. So then once it takes shape of a star, then as I said, it has a different masses. Consider this is the smallest mass where it has a fuel. Yeah, temperature is not sufficient enough to burn. So this will end up as a hydrogen ball. I mean, most of the thing is hydrogen and helium, but in its center it has a hydrogen. So it will end up as like this. So then these are all called as a brown dwarfs, which is very similar size of the planets. It's almost close to the planetary sizes. And then we come to the sun-like stars. And the sun-like stars will grow bigger as a giants. They are called red giants. Like sun will evolve to this size. Just for your information, this size is like a 10 times bigger than the sun now. So here already people started calling as an old age. So this is the place we will see nowadays only few planets that we see among these stars. So then there are a lot of claims comes that okay, some of the stars might have eaten by this. So now we are in 1 AU, right, distance. Imagine the sun just becomes double. We are nowhere in that way. So then these particular giants, if they are singles, then what they will do is that with time, the central part will be much gravitationally bounded, but then it will lose its envelopes. So that will just go away. So at some point, your gravity goes down and your radiation pressure goes up. So in that way, like it will just go away and then settle down as my surrounding material. This is called planetary nebulae. So this particular stars, whatever they produced, the elements, all varieties of elements it produces in its envelope, it will leave it to this particular nebulae. So researchers think that the planets or some of these metal-rich smaller objects can form from this nebulae. Okay, and after some time, the central part will stay back. That is, it was, I don't know, it working in a very deep. Okay, how can I go back? Okay. So the central part will stay back, which is a very dense one, that is called white dwarf, and it will lose its just material. Okay, I think by this evolution we can convince that whatever the material that the stars produces inside, at some point it keeps giving to the whatever the medium. Okay, it is like a kind of a cycle. And then again the stars, again when your material is there, then material again becomes like this. It's not a one star. So all the billions of the stars, it just born and die. It gives its material. And in the next generation will get much more elements. So that is the way, like in our universe, the metals are getting richer. And by the way, it's not the metal percentages is something like only a 3 or 4% compared to the hydrogen and helium. Okay, so even it gets richer and richer, it won't be much richer. But whatever the stars which born now must have a much more elements than what the previous generation stars. So this is all because of this cycle. So this is the way the cycle goes on for the lower mass stars. Like that, slightly, if the star can also be in a double system or triple system or the multiple system. Like this, our sun has a planetary system and multiple system. Like that, there must be like 3-4 stars together. So they are called binary systems, triple systems, multiple systems. So then if at all they are in the binary systems, so that's a complicated, no? So if you have siblings, you will be keep on fighting at one point. So it's like that when you have a binary system, it can be, it grows until a certain time, but then up beyond, oh, is it? Okay, then so after some time it will actually goes into a very violent phenomena. Okay, so this is the way, like the massive stars will go into very violent phenomena. Okay, so I didn't know that I took so much time, but I'll go faster. But then how do we study them? Okay, this is all about, we know that all these things. The easiest, the only way that we study is through the electromagnetic spectrum. And in the electromagnetic spectrum, you can see that from the ground, you can only see a certain band of light. And then for a certain band, we will have to go to the space. So in that way, you have a radio telescopes, you have a, you have radio telescopes, you have optical and IR telescopes, and some of this gamma ray telescopes and UV telescopes on the sky. So this is the way it is distributed, and all astronomers study the light in different electromagnetic ways in this way. And this is I think you have seen that this is our observatories in India, and this is another observatory which is at Monakia, which is in the northern hemisphere. Yeah, and this is another observatory where it is in the southern hemisphere. So yeah, I think you have seen this when we do the observations, and the first thing that we know is that we'll take a spectra, which but in our lab I think it will allow us white light kind of here, or to use some prisms and all, and then, but whereas in astronomy we do very high resolution. So this is the spectra. I think everyone knows that once we know the spectral line information, then we will go back and get its composition, and we also get the temperatures, which is about time, and we also get the gravity, which through the ionization, and various things. And once we know the position of the line, and we know that whether it shifted here or there, and also how much broadens it. So we'll get a lot of information from this spectrum. And if you see a star, actually star has a different motion. It just moves, it not just stays consistent. So you can see that, so there is a distance is very important from the sun to any star. And the star also moves in the transverse velocity, which is called the proper motion. And you have a line of sight velocity, which is called radial velocity, and you also call it the space velocity. So this is all the things that astronomers measure, and they understand the real motion of the star. And the distance is the standard parallax method. That means if we see today, we will see the stars in one direction, but then the far away stars in the same position. But then if I see after 6 months, then it looks like it is actually moved to a different place, but it is actually not. So that is the way you get the parallax angle, and that is the way you get your distances. It's very simple trigonometry. And then you will have a spectral line shifted towards a different wavelengths. So if it is kind of blue, blue shifted, and if towards red, it's called red shifted. So this is the way you understand that there is a velocities, which is line of sight velocities. And you know the spectral lines. If any material is moving too much faster, basically the spectral line will get broadened. But in our lab, we see that the spectral lines are very sharp because there is no velocity in perpendicular velocity. So that is another thing that we do. But then all the stars which I was just so far talking is all on the field. Okay, but they are all formed in these clouds, and then you can see that they are all in separate. Also, actually, majority of the stars actually form in groups. So they are called actually like clusters. So they are called open clusters, which are loosely bound. But whereas a globular clusters is called, it's actually a tightly bound, and then so many stars bound together. So field stars, a lot of globular clusters, a lot of open clusters. We just combine them. That is nothing but our Milky Way. So these are all the stars, clusters, and all this. They are all located in a different locations of the Milky Way. So you have a central very heavy mass over there, and you have these spiral arms, and our sun must be sitting somewhere here, and you have various places stars must be forming, and some places globular clusters, open clusters, all are. So basically this is defined as a disk, which is at the center, and you have a disk, and you have a halo. So this is the and central portion is called as a bulge. So this is a standard structure of the Milky Way, and you can see that in the Milky Way we have older stars and also the younger stars. And you see the disk, most of the disk is called as very young stars. But whereas in halo, called a population 2, they are very old stars. So by studying these young stars and the older stars, people try to understand the evolution of our Milky Way. And not just a Milky Way looks like this, and you have a varieties of galaxies, which is a different shape. It's actually the morphology is different, but your fundamental formation of the galaxies is very much similar. So this is actually there for illustration, but these are all real observations. People observe in different bands of electromagnetic spectrum and then combine together, and this is the way we get it. So basically in the night time, if we see, it also looks like a dot, but then you have to have deep observations of it. So this is, and people say that all this Milky Way, this forms in a very simple manner, that this is a all big giant molecular cloud, and then some of the stars grow and they basically explode and give the material to it, and they form your disk, bulge, and halo. That is the one scenario. But then another scenario, people think that there are small galaxies forms and they merge together, and they form as a bigger galaxies. So there are huge galaxies in just for your number, there are billions of stars and then millions of galaxies, just for to give you a flavor. I think I'll stop here. Thank you.
Any questions from the audience?
With the last point where you stopped, when two galaxies they combine, and we are expecting our galaxy to be merged with another one soon.
Not because the formation was like this. That our galaxy might have formed through the mergers, but there are two nearby galaxies, smaller galaxies, which we have like called large Magellanic Cloud and small Magellanic Cloud and Andromeda. But I think in a close lifetime,
No, that is
not.
fine.
But then in future, there is a possibility that they can again come into.
What my question was, suppose if we expect that that kind of merger is possible, what are the consequences? Like now the life is existing on the earth. If something is happening and combining like that, so it will be so spontaneous that we won't feel any effect on us, or how can you interpret when that merger happens, the effect on that on the earth?
See, actually, this is the one. Is not a cartoon. It is actually a real picture.
Yeah.
So it's like a real mergers happen. And what happens is that even a galaxy merges, and also the stars also gets merged. There is a one scenario, basically the heaviest stuff in a galaxy or a star is the central portion. So what happens in most of, at least the simulations people show is, they merge together at the center. But then it keeps its morphology not completely disturbed. There is a one scenario. Even in the star, it adds more mass at the center, but whereas your surroundings and then your envelope, it still stays, but there must be slight changes, not any major changes. That is the one scenario people could come up with. But if it is a very smaller galaxies, maybe it will disturb. It depends on the scale of those galaxy mergers and also the scale of the star mergers. But certainly there must be there will be an effect on it.
Sir, in the beginning you showed that 69% is the dark energy
Yeah.
and 31% is the dark matter.
Uh,
So dark energy means it is an unknown thing.
Dark matter is also
Unknown thing, right?
Yeah.
How we can say unknown thing is 31%? How we can predict it?
No, yeah, that is what that's very. People actually there are a lot of models. So that is the way they try to explain the. They add. See, for example, when I say dark, that means you don't know.
Yes.
So they add this much amount of energy and matter so that it will actually forms the entire universe. I mean to say, this dark matter or dark energy is not even, you can find it in the galaxy or in between the galaxies. People actually observe, expect certain amount of light to, it takes its own path. So when they do this experiment, they will see this lensing effect. There are multiple effects. It tells you that there is something which is making the light bend, or there are certain properties that this, and then they incorporate certain amount of energy and the matter, and that is the way people extrapolate that this much of amount of things that we don't know. Okay. Otherwise, what happens is that whatever you get, light has to take at certain time and certain path, right? So that is the way they understand that in between, whatever we see, the between galaxies or between stars or something, there is something which is hidden with energy. It has some energy, and energy just doesn't, without any matter, I think it doesn't. Yeah. So there is a lot of research goes on about this matter that we doesn't know. Not just baryons, you have various other matters. So this is different particle physics people, if you ask, I think you will have many various things come. So sometimes people, when there's a non-standard models also there, non-standard models to explain the universe. So there they will put all these varieties of particles, and then there's a lot of research, basic research is going on in the particle physics.
Any more questions?
Another question, I just sort of interact with you after this session. But for the benefit of all, I wanted to say, our understanding of the universe is maybe 100 years or 200 years, the modern science.
Modern science is maybe you take it up some 400, 500 years.
Okay, sir.
Take it.
And we have a history of 2000, 5000 years of civilizations,
Yeah.
all good civilizations. And I am of the opinion that the various metaphysical forms, maybe, put it in better, there could be better understanding of the universe which is not decoded. This is my firm belief. Just to conclude, I want to say just 2 weeks back I had 2 hours discussion with Dr. Kiran Kumar, our former chairman. So the theologies are not decoded properly, is my understanding.
I would say in other ways like transfer of knowledge.
Yes, sir.
So that transfer of knowledge has not reached to us. Maybe they are knowledgeable. That's what you are trying to say.
So like our own civilization,
Yeah.
sir.
That's what I'm saying. The knowledge which is there like 1000 years back, the people have a knowledge. That knowledge has not been transferred because of various reasons.
So actually decoding is good to say. Because
Also, if you are speaking about metaphysical things, like Indian philosophies and Western philosophies have their own.
No, no, for
aspect.
example, Aryabhatta. Aryabhatta, you see, all the great scientists of Indian heritage, they are not decoded. Our people are interested in studying astronomy and getting to some job. You see?
No, I think when you say decoded, what I'm trying to understand is actually they understand the universe in certain way.
Correct.
And they, whatever you call, they communicated that knowledge in a different form. Okay, that form is not
Yes, transfer.
transferred. I think now I'm seeing there are a lot of people who are trying to read the oldest scripts. At least in Bangalore, I'm hearing in some lectures where they are taking up this old scripts and then trying to understand what they try to say.
Sir, absolutely, sir. The previous speaker, for example, he mentioned about Oriental Research Institute. There are only scriptures of different, for example, I know Pali, there are 240 volumes. I mean, this is just to mention. Thank you.
We agree. Otherwise, there was so much of engineering was there too. They couldn't build the pyramids in such way. We agree. We
It
don't.
was a very good presentation, sir.
On the behalf of the department, we would like to thank Dr. Barat Kumar Yerra
Thank you for